Yes, I don't need that. Okay, it's 1:30 in your respective time zone. And we're going to start the session with Nicola Pinzani at Oxford, and he's going to talk about giving operational meaning to the superposition of causal orders. So take it away, Nicola.
Thank you, Matti. Good afternoon, everyone. So I'm going to talk about giving operational meaning to the superposition of causal orders. This is joint work with Stefano Gogioso. And okay, so what do we actually do? So we start by considering a probabilistic theory of processes which models the operational aspects of some physical theory, in our case, quantum theory. And we want to provide a sound way of constructing and characterizing localized processes which don't take place against a fixed causal background. And first, we need to digress a bit about the notion of control of processes in a general probabilistic theory. We are going to focus then the second part on this the notion of causal control, both in the classical and in the coherent case. And so the idea would be to construct the superposition, a concept of superposition of diagrams for these categorical probabilistic theories. Now, so the idea would be, okay, categorical probabilistic theories models the agent interaction, local agent interaction with some quantum system, with some inputs and outputs. And we want to add a controller, so someone who's able to control the order of those local agents and make it quantum. Okay, so the framework is therefore the one of a probabilistic theory, which is a strict symmetric monoidal category satisfying some additional requirements, so that there is a full symmetric monoidal category equivalent to the positive real matrices, which models the classical theory. It is enriched in commutative monoids, so we can take the sum of morphisms, and comes with an environment structure, which satisfies some requirements, so that it factors for these product systems, and it's equal to the empty diagram for the tensor unit. So the probabilistic theory most relevant to the work is quantum theory. Which is defined by taking completely positive maps with the quantum classical interface, with classical theory. So a general morphism, so a general map in this theory will look like this, where there are some classical systems X and Y and some non-classical systems A and B. So then we need the notion of a preparation and observation pair, which is a pair of processes, a preparation process and an observation process. So a process that goes from the classical to any other system, which is a kind of preparation, and an observation which goes to that system to the classical, which satisfy this property. So we compose them. This is the same as having the classical identity. So we are encoding some information and we are able to sharply recover it. Now, so what do we mean by control? So if you if we have a family of processes, so from A to B, not necessarily normalized or subnormalized, a controlled process for the family is defined as a tripole consisting of an SPO pair that I have defined before, and so P and M, preparation and measurement, and a process going from H tensor product A to H tensor product B, where H is the system to use to encode on the preparation, which satisfies the following graphical properties, so that when an agent acts with a preparation, everything decoheres, and the same is with the measurement. So this essentially signifies that an agent which is able to interact with a control system through a preparation and a measurement sees it as a kind of classical preparation and measurement. Is able to control, to choose a member of the family, and then to measure it, so to make sure that this is the kind of choice that happened. So in general, in categorical probabilistic theory, a notion of control always exists for an arbitrary family of processes. And this is the classical control, which is described in this way. So basically, H is now equal to X, and the morphisms, so the SPO pair, is given by the identity on the classical system. This is modeling the notion that we can unambiguously talk about, an agent which is kind of preparing a transformation from a given family, from a chosen family, and then actually realizes what he has applied, so measures what he has applied unambiguously. So this is a kind of classical control, no? But in quantum theory, we know that there is a notion of coherent control. So if you give me a family of pure, completely positive maps, I can define a coherently controlled process, which we'll denote in this way, which is a kind of a generalization of the control knot. And well, it's simply, like the SPO pair is given by a measurement and preparation in a fixed or normal basis. And then this map, we show in the paper that it's kind of canonical up to an arbitrary choice of the phase. So it's the only control process that, which is not the classical one, that can be constructed. It's a canonical way, in a canonical way up to a phase. Now, this is for pure CP maps. What about for arbitrary? So if you give me an arbitrary family of transformations of morphisms in my category, can I construct such a notion of control? And this is generally not possible. Not possible in a sense, like it is not possible to assign it as a function of the family of maps. Okay, to assign a given control as a function of the family of maps. This is because, like, one way to construct it would be, okay, you give me a purification for each member of the family over the same environment, and then I take the kind of canonical control that we had described earlier. And however, this is not going to be like, if you give me another purification of the same family, then every member will differ by a unitary applied to the environment. And we cannot construct a map which has this kind of symmetry, so which is independent of this application of controlled unitary on the environment. So this canonicity breaks down. But I promise to talk about causality. So a definite causal scenario is, because we need to talk about the notion of control of causal orders. So a definite causal scenario is a triple given like gamma ENO given of a cyclic frame multigraph gamma. I'll explain it later what I mean really. And an assignment for every node of the graph of a finite set of classical inputs, so the values available locally to control the process at the event, and a finite set of classical outputs, so the values that the process at the event can return locally as a kind of outcome. So it's a kind of classical backbone of the experimental scenario. Okay, you have the causal structure, and then all the kind of classical inputs and the classical outputs, so this is like a definite causal scenario. So it's on a cyclic directed graph. Note that there are some nodes which form the kind of input node and some output nodes, which are just defined to make everything compositional. But we are interested about the internal nodes, and those internal nodes are going to be called events. Framing just means that basically we give a total order on the incoming and outgoing edges for every event. Moreover, on the event, we assign the kind of classical data of the input and the output for each node. So this is a definite causal scenario. So this provides a semantics for certain diagrams. And how do we make them? Well, we create a diagram over this causal scenario. A diagram over this causal scenario is an abstract association of systems of the category for the edges, and then kind of morphisms which are compatible with the assigned systems. So what we do is effectively associating to every vertex kind of, if we speak in quantum, a quantum instrument which is compatible with kind of the local description. So the input, the local input, the local outputs, and then the systems. Then there is a unique way, it's a symmetric monoidal category, there is a unique way to extract a morphism from this evolution. And this morphism shown on the right. And this is the kind of the interpretation of a diagram over a definite causal scenario. But we want to pass to kind of the indefinite case. In the indefinite causal scenario, so we have a set of events, which are those internal nodes, and we don't have an underlying graph, causal graph anymore, but we choose a set of symbols and associate to each event some totally ordered set of input and output symbols, and also to the kind of initial and final boundary. This is the kind of abstract operation description of what happens locally. And the association of symbols, it's kind of guarantees that the kind of system is always, that the system that will be associated to that half edge, in a way, will be the same across the experiment, if you wish. And then, like, there are several definite causal scenarios, so there are several ways to construct a causal graph joining the half edges. And this will form a kind of a causal, a classical state space of all the kind of causal possibilities of kind of joining the diagrams, or kind of gluing diagrams together, and are shown, for example, here now in the slide. So let me give you an example. And then we want to see, like, what does it mean to interpret, to have a diagram over an indefinite causal scenario? Well, as before, we associate not anymore to edges, but we associate to symbols a particular system, that one that is going to be guaranteed to be the same across the experiment, and then to the vertices, a general map of the correct type again. And I forgot to mention that even in the indefinite causal scenarios, we always specify in the internal nodes a set of inputs and a set of outputs. Classical. Then this induces like different possible transformation, one for each kind of definite causal scenario compatible with the indefinite causal scenario. Those are shown on the right. So how do we interpret then those kind of indefinite causal scenarios as kind of controlled superposition of different causal orders? Let's consider the case of the quantum switch. So in the quantum switch, we have two events, alpha and beta. We have only one system, which is guaranteed to be the same for all the kind of local description. And then we put some input and some set kind of describing the local input and the local outputs. And we associate to the nodes a quantum instrument. Know that this is an arbitrary quantum instrument. So for now, we choose a kind of an arbitrary purification. And this is the kind of discarded environment that is shown in the picture. So this is therefore the association of a diagram over an indefinite causal scenario. Now, how do we make then the kind of controlled version? How do we control the different possible evolutions? Well, for every output and input, there will be a pure map for each choice of quantum instrument, and those kind of pure maps can be composed according to the different definite causal orders compatible with the indefinite causal scenario, and then we take the control of them. We take the canonical control of the purifications, and then we discard the environment. summing over all the inputs and the outputs, we get our map here, which is the controlled kind of causal order. But now we have shown that in fact this is not in general well defined for CP maps, because we have to choose our purification. But it turns out that for causal ordering, so for general causal ordering, this is not only for the switch. Indeed, everything can be made general, and it's made general in the paper. There is an independence on the choice of purification. This is like, if you give me any other purification for the quantum instrument, this will differ by a kind of unitary transformation on the environment. And this unitary will be appears in all the branches of the superposition. We can pull the environment out, take the coherent control, and discard the unitaries, and we get the same map. Okay. So what we therefore show is that, like, given an indefinite causal scenario and a diagram over this in quantum theory, so for each possible choice of the phase gate and for the computational basis of with dimension given by all possible definite causal scenario compatible with indefinite causal scenario, the coherent control is well defined independently of the choice of purification. And we can have an idea of the agent which is controlling this degree of freedom, this causal degree of freedom, while there are those kind of laboratories manipulating the input and output locally. And this is a kind of a canonical construction in a way. But what is then a superposition of causal order? We can immediately read out what a superposition of causal order is. So given an indefinite causal scenario and a diagram over it, by a superposition of causal order with a given phase, we mean the quantum instrument obtained by considering the coherent control, which is constructed in the way I described earlier in general for general indefinite causal scenarios. And then precomposing the control system with the kind of uniform superposition state given below. Recall the kind of for every map associated to a definite causal order, there is an element in the basis which refers to it, in the kind of basis of the SPO pair of the orthonormal base. And then we post-compose the control system with some measurement unbiased with respect to this basis. And then we get actually for example, a notion of the quantum switch, or we can generalize the notion of the quantum switch by taking more events in the indefinite causal scenario. And so if the agent then discards the controlling system, what we get is a kind of non-coherent so super probabilistic distribution of all the possible causal evolutions. So this refers to the fact that discarding, which is actually a kind of an epistemic process in a way, tells us that the information about the causal order is still hidden somewhere, but not accessible to the agent. In order to create the real superposition, we need to post-composing with some measurement unbiased with the computational basis, so to erase the quantum information about the order. And yeah, in the same way, okay, so this construction that I presented, this interpretation allows you to interpret, so can be made totally compositional in a way, because it's based on these categorical principles. And one can also think about preparing different kind of mixture of causal orders, but this is always well defined, like not only like coherent mixtures, but also using the preparation measurement to kind of create a kind of probabilistic mixtures of them. And yes, and this is all. Thank you very much. Matti?
Yeah, sorry, I just had to clap. Now, thanks, Nicola, for that really interesting talk. So I'll ask the questions out loud, but I'll also post them into the chat as well. So the first question is from Villasini, is how do you model dynamic causal orders in this framework? Do you simply add that party's local input as a control in the diagram?
So there is this external system which encodes there is an agent which is able to choose a particular causal order, but he also kind of can prepare a kind of precompose with a uniform superposition state and obtain a kind of superposition of causal orders. It's just another agent. It adds in the diagram another agent which is able to control this additional system that we have introduced, and this additional system will control the wirings of the diagram essentially. So yeah, I don't know if I have answered the question specifically, but so we take a kind of general kind of probabilistic theory, and we add the possibility that there is this kind of agent which controls the causal order.
The next question is from Tomasz. It says, since the boundary nodes seem to be of different nature than the internal ones, can one think of the definite causal networks as some sort of structured cospans?
So I haven't really thought about this, but I guess that yeah, like the compositional nature of those causal diagrams, like the categorical nature of those diagrams can probably be described in this way. Yes, but you can also think of you can think of them as half edges. So you can compose the diagrams and remove the vertex.
Okay. Fabio's got a question, which is, wouldn't you rather call that entanglement of causal order with a control? I'm not sure what that specific to you.
No, like no, really.
Oh, right, yeah.
You can. I mean, you can reconstruct the switch in the same way. So you precompose it with a uniform superposition state, and you have the switch. So a superposition of different causal orders. Like this is entirely compositional, so one can think of situation where you have two kind of indefinite causal scenarios, and then the actual system that is used to control the kind of possible causal orders of both of them can be it's actually kind of a product system, and one can entangle the two causal orders. So we would have a kind of two switches with entangled causal orderings. But essentially, like this entire framework is used to, like if I put kind of a state in the initial boundary and then I discard everything else. If I keep the kind of classical wires, I get a kind of probability table of correlation between inputs and outputs. Locally, those correlations are given by the quantum instrument, and then like we have given a semantics to a kind of a broader class of correlations. So to ones that arise from this kind of quantum network of agents acting locally.
Okay. I think Pablo asked a question that's generating quite a lot of replies. So maybe you might want to quickly say something now, but I think there's already been a few responses from Stefano, and that is, this seems to resolve the problem raised by Cyril Mehdi and Alastrabot and Vex of the ambiguity of controlled CPTs.
It's a form of mathematical statement. It tells you where the ambiguity lies, in fact, and yeah, it explains what it means.
Okay.
But however, like superposition of causal orders are well defined and are independent of the choice of purification for any kind of network. Can you give me kind of general indefinite causal scenarios? Then there are the definite causal scenarios, so the graphs compatible with it. You assign the local operations, and then this will always be independent on the choice of purification.
Okay, let's have a look. So, okay, there's a bit of follow-up to Fabio's question, but yeah, okay, there's plenty of opportunity to dip into the Slack and respond to some of these questions. But in the meantime, I'm going to do another clap and thank Nicola again.
Thank you very much, Matti.
All right, and I'm going to move on to the next talk. Thanks, Nicola.
Thank you. Bye-bye.